Good morning, class. Yesterday we have done the image formation by concave lens. We have seen there are basically three cases for image formation, and the image formation by convex lens we have already done. Today we will do a very important topic in this chapter known as lens formula. So this part is sign conventions and lens formula. Now you must have understood what is lens formula. Like in the class 9th you have done a mirror formula that was 1 upon v plus 1 upon u equals to 1 upon n. Similarly here we have lens formula. Now if you remember, you have in the class 9th there are some sign convention to measure the value of v, u and f. You already know what is the meaning of v here. V is the basically image distance, u is the object distance and f is the focal length. Okay, so to measure these quantity we use a certain rules. Sometimes the quantity can be negative and sometimes it can be positive, right? So what are the rule of and basically how we measure these quantity, right? So let's start with sign convention. All right. First, there are some assumption that we have make to understand the lens formula. The first assumption is the lens is very thin, right? Lens is very thin, so that the distance from the pole, distance taken from the pole or taken from the optical center, they will be equal, right? This is the first assumption. And second assumption is all the distances are measured from the optical center. The optical center. All the distances are measured from the optical center, right? Like if you have, like this is the convex lens, so here it will be the optical center O. Second assumption, object is always placed on the left side of the lens. That means object is always somewhere here. It will never be on the other side. Now the time of sign convention. Light will go in this direction, right? This is the direction of light. This is the direction of incident ray. So all the distances measured in the direction of incident ray will be taken as positive. All distances in the direction of incident ray will be positive and vice versa. That means opposite to it, it will be negative, right? Above the principal axis it will be positive and below the principal axis negative. Distance or height above principal axis is positive and below principal axis is negative. So these are the sign convention while using the lens formula. Right, let's understand this with the help of ray diagram first. Is the convex lens. Either you can take convex or concave, the sign convention for both are same. Here the optical center, let's say it's the object AB or O. Right, object is basically denoted by the O. Now, light is going in this direction. So all the distances you measured in this direction will be positive, and in this direction it will be negative. All the distances upward will be positive, and all the distances below it will be negative. As simple as that. You can learn this with the help of Cartesian plane. You must have used the graph paper, and in the graph paper we have 4 quadrants. Here it is x, y, minus x and minus y. And the distance are always measured from the center. Here this center is optical center. So if you are going in this direction, we know that x will be positive. If you are going up, you know that y will be positive. If you are going on the left hand side, here it will be x will be negative, and if you are going downwards, y will be negative. So it's just the same thing as we use in the graph paper, right? So now let's write the lens formula. Lens formula. Lens formula is 1 upon V minus 1 upon U equals to 1 upon F. Here V is the image distance, U is the object distance, and F is focal length. F is the focal length. Okay, so these are the some terms. Now when we say focal length, we always meant it by the principal focal length or the secondary focal length. So I'm writing here U is always negative, because obviously it is always on the left hand side, right? V can be positive or negative depending upon the where the image is situated. Like if we take the example of convex lens, the last part, when the object placed between the focus and the optical center, the image is formed on the this side, on the same side of the object. So V can be negative. And in all other cases, the image formed on the other side of the lens, so V will be positive. So V can be positive and V can be negative. What about the focal length? Okay, so when we talk about the focal length, here is the focal length, focus f2 of the convex. So this will be the secondary focal length, or simply f of the convex. So for convex, I'm writing here for convex, f is positive. But for concave, f is here. So for concave, f is negative. So please take care of these things while you solve the numerical, which is positive, which is negative, because if you put the wrong sign, even if you apply the right formula, the numerical will be wrong. Right? So please take care of it. The derivation of focal length is not included in your syllabus, so we are not doing it. You just have to remember the formula and some numerical based on this formula. Okay. Next topic is linear magnification. Linear magnification. You must have studied this topic in class 9 also. What was this? It is defined as a ratio of the image of height to the image of object. It is defined as the height of image to the height of object. Right? That means m equals to I upon O. When you solve the formula, which is again the derivation, which is not in your syllabus, you find this I upon O is also equals to image distance upon object distance, that is V upon U. So now M have two formulas. First I upon O, which is a general formula, and also V upon U. So this is the formula for linear magnification. As you can see here, it is the ratio of the same quantity, height of image, height of object, both the ratio of the heights, so there will be no unit. Alright, now this is a very important thing about the linear magnification. By just seeing the linear magnification value, you can tell the characteristics of the image. See how? If M is negative, it shows that image is real, right? And if magnitude of M is more than 1, then obviously image is enlarged. If M is positive, it means image is virtual, and if the magnitude of M is less than 1, then image is diminished. That means smaller the size of the object, and obviously if M is equal to 1, that means image and object are of same size. Okay, M negative means real, M positive means virtual. If M is more than 1, like 1, 2, 3, 4, or 2, 3, 4 and all, it means image is magnified. If it is less than 1, like 0.5, 0.6, 0.8, that means image is diminished. And obviously it equals to 1, image is equal to the size of the object. Sometimes people get confused, see in the value of M, like suppose the value of M is -2. Now it is clear from the minus that image is real. Now people think that this is -2. -2 is less than 1 because -2 is below the 0. But here we are not taking the sign. Sign is just to show the whether is the image is real or virtual. So we'll just see the value, the magnitude. So 2 is means it is enlarged. So don't confuse in this. Will this minus or plus just show to show the real or virtual, and this is plus 1, 2, 3, 4 will show the enlargement or the diminish or equal to the size of the object. Right? This is your magnification. Next topic is power of the lens. The deviation of incident light rays produced by a lens on refraction through it is a measure of its power. It means how quickly a lens bends the light. If it bends the light very quickly, that means power is more. If it bends after some time or it will take a distance to bend, it means the power of lens is less. Let's take 2 examples. We have considered 2 lenses, right? Once the parallel rays come, it bend like this, and here it deviated. But in this case, it bend like this. So because this is parallel ray, so this will be the focal length. Let's say this is f1, and here this is the f2. Now which lens is deviating the light quickly? Second lens. That means the power of this lens will be more than with the first lens. In the second lens, f2 is less. In the first, f1 is more. So that means the relation between f2 and f1 is inverse. Because here power is more but focal length is less, and here focal length is more but power is less. So what will be the relation between the power and the focal length? The power of the focal length P is equals to 1 upon F. But the condition is F must be measured in meters. Then power will be in diopter. This is the unit of the power of lens. In short, it is D. Alright. As we know that the focal length of concave for convex, F is positive, therefore power is also positive, and for concave, F was negative, hence power is also negative. Right, so whenever you see a positive power, that means the lens is convex, and when you see the negative power, that means that the lens is concave. Right? Suppose we have a power of -5 diopter. That means this is the concave lens. And suppose we have power of, let's say, +2, then this is the convex lens. So we have completed our chapter. In the next video, we will discuss some very important numerical based on the lens formula and the power of lens. Till then class, thank you so much.